All right, we're nearing the finish line here, video number 7, and we're going to go through questions 38 through 41. Starting off with the relationship between bond length, bond energy, and strength of bond. Bond length is just how long the bond is. What is the distance of the actual bond itself? Bond energy is the energy required to break the bond. How much energy is going to take to do that? And then strength of bond is just how strong the bond is itself. Now, the strength of bond and bond energy, that is a direct relationship. So the stronger the bond is, the more energy it's going to take to break it. Now, as far as bond length goes, the longer the bond is compared to a shorter bond, this one is going to be easier to break. So it has less bond energy. So when the bond length increases, increased length, then the bond energy goes down. And therefore, so does the strength. And so when we look at that, there's an inverse relationship between length and energy and length and strength. There is a direct relationship with energy and strength itself. So then the opposite is true as well. As the length goes down, then that makes for a stronger bond, so increase on the strength, and therefore the energy is going to increase. It's going to take more energy to break that bond. Okay? All right, the next one. What type of bond, nonpolar, polar, or ionic, exists in the following? Explain the meaning of each one. Now, with this one, remember that we should be remembering a few numbers. It would be 0, 0.4, and 1.7. So if we fall between 0 to 0.4, that's one thing. If it's between 0.4 and 1.7, it is another thing. And if it's 1.7 or greater, then it's another. So if it's the electronegativity differences, that's what we're looking at here. The electronegativity difference is greater than 1.7, then it's ionic. If it's in that middle ground there, then that is a polar covalent. And then if it's real low there, the difference between them is going to be nonpolar. Okay, so on the first one we have hydrogen and fluorine. What we'd have to look up is the electronegativity difference. And at this one it's going to fall between 0 and 1.7. Now I don't actually have the numbers for you on this one. But on the test, we're going to provide those numbers for you, either on the test itself or in a table, so you can look them up. So you'd look up the electronegativities of the two, hydrogen and fluorine, and in this case, when you subtract the two, you would find that there's a difference between 0.4 and 1.7, so therefore, this one would be polar. Okay, the next one is a metal, non-metal. So just based on that alone, we would probably expect that to be an ionic one. And if you look up their electronegativity differences, what you would see is that it's going to be greater than 1.7. And again, I don't have the numbers to provide here for you, but that's what you would get if you subtracted those numbers. And for that reason, again, not just because it's metal, non-metal, but for that reason, it's going to be ionic. And on the final one, anytime you have the same two atoms that you're going to combine, it doesn't matter what their electronegativities are, the difference between them is going to be 0. And so those two ones are going to be nonpolar. Now, again, I think at this point it might be really important to just kind of quickly go over what does it mean to be nonpolar versus polar. Now, in both of those here, that means they're going to be sharing. Those are covalent substances there. So they're sharing their electrons. Whereas the polar is sharing, but they're sharing unequally. So the electrons are spending more time on one side of the molecule than the other, and what happens is you end up with one side of it being slightly positive and the other side of the molecule being slightly negative. Whereas a nonpolar, they're sharing that equal. Those electrons are being shared equally, and the overall charge of the molecule is going to be neutral. And then with ionic, like we said before, that is just simply not sharing, that is a transfer of electrons. Okay, and for the last part of this one, the big chunk that's left over here, we're going to draw Lewis structures for the molecules, and we're going to identify their shape, and we're also going to talk whether the molecule itself is polar or nonpolar. Okay, when you do these problems, now remember we're going to list out the elements. So silicon and chlorine, you're going to count the number of atoms for each one, and then you're going to multiply by the number of valence electrons for that given element by looking it up in the group that it's in. So silicon is in group 14, so it has 4 valence electrons, and chlorine is in group 17, so it has 7 valence electrons. So multiply those numbers out, and I'll give you the grand total of electrons for that specific type of element. So we're going to get a grand total then when we add them up for the molecule itself. It's going to be 32. Now, when we draw the Lewis structures, the rules are put the element that's the lowest in number in the middle, or if it's carbon, put carbon. So we have silicon, and then surround it with those terminal atoms, which in this case would be 4 chlorines. Now these single lines represent all single bonds and represent 2 electrons for each one. So we have placed 2, 4, 6, 8 electrons. So the original count was 32. Now I'm down to needing 24. Now I won't place any more in the central until I've filled up all of these other terminals, and I place them 2 at a time, again like I'm dealing out a deck of cards. And you deal them out fairly like so. And then just keep going around until you run out. So I just placed 8 more, so that means I'm down to 16. So 2, 2, 2, 2. I placed 6 more, now I'm down to 8, and that means 2 for each of those terminals. Now the goal is for all of the terminals and even the central to reach that octet rule. So now count them up, 2, 4, 6, 8. 6 of their own, 2 that are shared for each one of these. So all of the chlorines are good. And the silicone has 2, 4, 6, 8 that it's sharing. So now this is a stable configuration. Now when you look at this, when we have one central atom bonded with 4 terminals, then that is called the tetrahedral. Oh, pen isn't working very well there. Tetrahedral. And I see here that I have symmetry. I have no unshared pairs of electrons on the central. We have terminal atoms, all 4 of them being the same. So this is a non-polar molecule. The next one we have CO2. So I'm going to list out the elements, count the number of atoms, multiply by the valence electrons that they have, and then add them up after I've multiplied. So 4 plus 12 is 16. Alright, so I need to place 16 electrons. Carbon is the central, not only because it's carbon, but it's the lowest number. And bonded to that are going to be 2 oxygen atoms. Alright, now with those 2 lines, I've placed 4 electrons. So that means I have a total of 12 remaining. And I'm going to place them 2 at a time on those terminals until I run out. So 2, 4, 6, 8, 10, and 12. So now I've placed all of them. 2, 4, 6, 8, 10, 12, 14, 16. All 16 electrons placed. Ask yourself, is everybody stable with 8 valence electrons? So 2, 4, 6, 8. The oxygen's happy. 2, 4, 6, 8. This oxygen's happy. But the carbon is left with 2, 4. So that one is not okay yet. So what I need to do is I need to take now from this one of these oxygen atoms and use them from take them from being unshared to being a shared pair. So I'm going to bring those 2 electrons down here, and when I do, I want to make sure that I erase them from up here. Now this oxygen has not reduced its number of electrons, still has 2, 4 of its own plus the 2, 4 that it's sharing. Okay, so that one's still good. This oxygen is still good. Now what about that carbon? So now it has 2, 4, 6. It's still not okay. So now what I need to do is I need to bring in another pair of electrons from this other one. So I'll bring that down here, form another double bond, and erase those. So now I have 2, 4, 6, 8, 10, 12, 14, 16, still the same number of electrons placed. And the carbon has 2, 4, 6, 8, and all the oxygens have 8 as well. Okay? Now, because I have 2 terminals atoms and no unshared pairs on the central, then that would make this a linear molecule. And all linear molecules are nonpolar, symmetrical. All right, the final one here. This one's a little different because it's an ion. It's got a charge to it, but I still do the same process. List them out. Number of atoms times the group number. Multiply those out. And I get a total of 25 electrons I need to place. Now, here's the trick though with this one. I have a negative charge, so that means I have one more negative than I would on a neutral. So in this case, I need to add 1 to my total, so I need to place 26 for the grand total. Chlorine will be the central atom. Bonded to that will be 3 oxygen atoms. I have now placed 2, 4, 6 electrons, so I need 20 more. So 2 at a time, dealing out those electrons to those terminals until I run out or until they're satisfied. Okay, so now all the terminals are okay. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. But when you take the grand total, what I'm at right now is 24. I still have 2 more electrons I haven't placed, but the terminals are okay. So if I have those extra ones and the central atom has room for them, now I will place them as unshared on the central. Now everybody's okay. The chlorine has 2, 4, 6, and 2 of its own 8, and so do the oxygens. And now the final step is anytime I have a charge, I need to put the whole thing in brackets and then put the charge outside of those brackets. Okay, the shape. I have 3 terminal atoms and I have an unshared pair. That's going to cause it to bend down. So it's going to be the trigonal pyramidal. Again, my favorite one to say. And because of this unshared pair here, we're not going to have the symmetry that we're looking for in the nonpolar. So this is going to be a polar molecule. All right, last question on this page here is what we want to do is in the following equation, just circle the products. And again, I hope by now this is easy. The reactants are on the left and the products are on the right. So we want to circle the sugar and the oxygen. That is the end of video 7, and we just have one more to go. Video 8 coming up now.